Thank you. So,
But people are still coming in.
okay, so should
Try
I
to
wait
come
a
in
couple of minutes?
efficiently and look for empty seats.
I'll just wait a minute, maybe.
Okay, I guess this is take 2. So Simone Giombi will be continuing with the second lecture on higher spins.
Okay, thank you. So let's continue from where we left yesterday. So yesterday we discussed how free ON or UN vector models in 3 dimensions have precisely the right spectrum of operators to be dual to higher spin theories in AdS4 of the Vasiliev type, which we haven't described in detail yet. We also mentioned that you can have not just free vector model, but also critical vector model if you consider the Wilson-Fisher interacting fixed point, and that on the AdS side should correspond to changing boundary conditions for the bulk scalar field. Okay. So we also briefly mentioned yesterday the case of fermions. So let me just briefly go over that. In D equal 3 or in any dimension, we can also consider a free fermion theory, of course. It's also a nice CFT. So let's briefly discuss that. Let me take n free Dirac fermions with a UN symmetry. So this is the free Dirac action. I could write it down in any dimension. I'm just specializing to D equal 3 here. And so since this is a free CFT, as in the case of the scalar theory we discussed yesterday, we expect that there are an infinite tower of conserved higher spin currents in this theory. And indeed, one can find them. Just schematically, let me write them down. So this theory has the following operators. So again, this is just meant to be schematic. There is one gamma matrix and that's minus 1 derivatives. So this is a little different from the expression we saw yesterday for scalars, where we have S derivatives and bilinear scalars. Here we have S minus 1 derivatives, so that the dimension of these currents is again S plus 1, as it's supposed to be for a conserved current in 3-dimensional CFT. So again, these currents are conserved. The dimension is S plus 1 because in 3 dimensions the fermions have dimension 1, as you can see from the Lagrangian. And then again, in addition to this operator, there is this scalar operator of dimension 2 now. Well, in the free scalar theory that we saw yesterday, there was a scalar operator of dimension 1. Here we have a scalar operator of dimension 2. So by the same arguments I was giving, well, first let me say that these are all the single trace operators of the theory. that we have in 3 dimensions. By the same arguments discussed yesterday, you expect that the dynamics of these operators, their correlation functions, should be described by a dual theory in AdS, which is again in higher spin theory, where these conserved currents correspond to some higher spin gauge fields, and this scalar operator corresponds to some bulk scalar field. Okay? But there is a difference compared to the scalar case that I was discussing yesterday, in that this scalar operator is a pseudoscalar. So the mass term in 3 dimensions is parity odd. So this is a parity odd operator, and it's supposed to be dual to a parity to a pseudoscalar in AdS4. So the dual of this theory, whatever it is, should be already different in the spectrum compared to the scalar theory I was discussing yesterday. And that's not the only difference. Also, if you look at correlation functions of these operators, they are different from the one of the scalar theory. For example, take the 3-point function of the stress tensor. This we already discussed yesterday. If just in this CFT, this free fermion, you calculate this TTT correlation function, this is different from the one of the free scalar, which we already also discussed yesterday, because I said that in a general CFT, TTT is a linear combination of these 2 structures, which are 2 different structures. So in particular, the cubic coupling of the dual theory to this CFT is different from the cubic coupling of the one dual to the scalars. So there should be 2 inequivalent higher spin theories in AdS4. One should be dual to the scalars that I was discussing yesterday, and one should be dual to this theory. So yesterday I was just talking about Poissonic Vasiliev theory in AdS4 as if there was only one, but to be more precise, there are actually two Vasiliev theories in AdS4 which preserve parity. They are called type A and type B, and the spectrum differ precisely in this way, that one has a pseudoscalar and one has a scalar, and the interactions are different. Okay. So indeed, this is, I will define later today what is this type B theory. So this is supposed to be dual to type B theory, type B Vasiliev theory. Dual to free fermions, UN or ON, depending on whether you consider Dirac or Majorana fermions. And the one I discussed yesterday is the type A dual to free or critical scalars. So while the conjecture that type A is dual to free scalar was made by Klebanov and Polyakov, this extension of that conjecture was made first by Setskin, Sandel, and Lee and Petko, who realized that there is this type B version of Vasiliev theory, and it has precisely the right structure to be dual to this. Okay? So here I wrote free, but as we discussed yesterday, you can also imagine that we can consider an interacting theory similar to what we were discussing yesterday for the scalars. So we can also have a critical, free or critical fermions. And again, the way that you can get interacting theory you can consider the Gros-Nouveau model, where you add quartic interaction. Then, unlike the case of the scalar that we discussed yesterday, this quartic interaction is irrelevant in dimensions between 2 and 4. But if you analyze this theory in the large N expansion, you see that there is a UV fixed point. It's UV because it's irrelevant, so there is no IR fixed point here. So there is a UV fixed point where the dimension of the scalar operator goes from 2 to 1, and the higher spin currents, as in the case of the Wilson-Fisher fixed point, are still approximately conserved. So the dimension is S plus 1 plus 1 over n corrections. So again, because this is a type of double trace deformation of our model, in the bulk what this corresponds to is changing boundary conditions for the field in the bulk which is dual to this operator. So in this case, delta equal 2 boundary condition corresponds to the free theory, and delta equal 1 boundary condition corresponds to the interacting theory. Okay? Let me just mention here that as Igor mentioned in his talk, there is a perhaps also nicer description of this fixed point, which is as a conventional IR fixed point of a different theory, which is a Grosnow-Yukawa theory. This is just a parenthetical remark. So we can describe this fixed point starting from this model. So we start with a theory which has n fermions plus 1 extra massless scalar with some interactions. Which are the only marginal interaction which are marginal and equal 4, consistent with the symmetry. And then you can develop a 4 minus epsilon expansion similar to the Wilson-Fisher fixed point. These interactions are relevant in dimension below 4. So you expect that this theory with this interaction flows from a free UV fixed point, which is a free theory of n fermions plus 1 scalar, to an interacting fixed point. And this interacting fixed point can be shown to be equivalent to the UV fixed point of this model. Yes?
Why did you exclude a mass for the sigma in that particular Lagrangian? Want to be generated by RG flow?
Yes, you want to describe CFT. So the mass we tune to 0 so that we have a conformal field here. You can start with 0 mass and use a regularization where this kind of, because it's not a marginal term, it's a relevant term, you can tune it. Yes?
Well, so there has to be therefore a relevant operator also in this description, but maybe it's harder to see because that description
Yeah.
is superficial or unwise.
Right. But the statement is that the fixed points describe the same CFT. So you can compare, for example, operator dimensions or correlation functions, and they are the same. Here you can do 1 over n expansion in any dimension. Here you can do 4 minus epsilon expansion to any order that you want for finite n, and then see that the two things always give the same result. Okay, so here we have an IR fixed point, which is supposed to be equivalent to that UV fixed point. This is just something that maybe is not very well known, but it's perhaps a more satisfactory way of describing this fixed point because it's a conventional flow from a free UV theory to an IR interacting theory, much like the Wilson-Fisher fixed point. Okay. In any case, it's clear from this description that since in this description this is a double trace deformation, we know what to do in the bulk, in the 1 over n expansion. We are changing the boundary condition for the scalar field. Okay. Any questions about this? Okay. Let me also mention something else. So while the free scalar theory is, so we discussed it in equal 3 yesterday. We could discuss it in any dimension, and everything I said yesterday could be repeated in any dimension. The spectrum is always given by totally symmetric traceless conserved currents plus 1 scalar. That's true in any dimension. This fermion model is a little different. So it's only in D equal 3 that the spectrum is very similar to the scalar theory. If you go to general dimension, there are more operators. For example, in D equal 4, there is an extra operator like this, which in D equal 3 is not independent because this is related by duality to a single gamma mu. And there are in general operators with many derivatives. So besides those, there are also these, which are dual to mixed symmetry. Mixed symmetry, higher spin fields. In this case, in AdS 5. You can do this in any dimension. Go higher and higher, you have more and more operators because you can put several of these gammas together. So in general dimension, this free fermion theory is not dual to a Vasiliev theory which is currently known. It's some theory which include regular totally symmetric fields plus mixed symmetry fields, and a nonlinear Vasiliev theory for this kind of higher spin fields is not known. Okay? While for the scalars, which is what we call type A, there is a uniform generalization to all dimensions, which is known. Okay? Any questions? Okay. So it just means, okay, let me schematically do something like this. So an operator like this would correspond to a Young tableau of this type. So it's not totally symmetric, and we call it mixed, usually called mixed symmetry. It is symmetric under these indices and anti-symmetric here. It corresponds to this Young tableau. While the simplest type of higher spin fields are the ones which are totally symmetric. Okay. Yes? A little bigger, okay. This? Oh, in general. In general. All right, bigger. Okay. Okay. So do you have problems seeing from up there? A little bit? Okay. Okay, so let me go here. And before we move on, just write down a table summarizing all the dualities that we've discussed so far. Okay, so I'll call this the Klebanov-Polyakov, Setskin, Sandel, Lee, Petko dualities. Okay, so we have bigger Vasiliev type A, Vasiliev type B, and here we have the choice of boundary conditions for the scalar field. Yeah, I should say that since in this, both in the scalar and the fermion model, the dimension is either 1 or 2, the bulk scalar field always has the same mass, which is m squared equal minus 2, as we discussed yesterday. But it's a pseudo-scalar in type A, and it's a regular scalar in type, the other way around. It's a pseudo-scalar in type B and a regular scalar in type A. Okay, so if we choose delta equal 1 here, we're discussing the free scalar. And here we're discussing the critical scalar. And here the situation is just reversed, as we discussed. So delta equal 1 corresponds to the critical fermion, which is either the UV fixed point of Gross-Nouveau or the IR fixed point of this Gross-Nouveau-Yukawa model. And for delta equal 2, we are discussing the free fermion. Okay? So that's a summary of what we discussed so far. So any questions about the table? One can also play with the changing boundary conditions for fields of higher spin. If you change boundary condition for fields of spin 1, that means that you are adding a double trace deformation, which is the square of the spin 1 current. And if you introduce the Hubbard-Stratonovich auxiliary field, that can be seen to be related to a critical QED model coupled to the N fermions. So that's also another theory that you can describe in the same framework. Okay. Okay, so before we move on to describe, hopefully to reach the structure of Vasiliev theory, let me finish by just making a couple of comments. So first, we already said yesterday, but let me say it again, why we are considering vector models. So the reason we're considering vector models, as we discussed yesterday, is that the spectrum of single trace operators, UN invariant or ON invariant, is very simple. They're just bilinears. Okay, so only bilinears. And so these single trace objects are dual to the single particle states in the bulk. If we have objects with more than two of these fields, like phi I, phi j, let's say I put some derivative, phi j, this is to be viewed as a, in this case, double trace object, or in general multi-trace object. It will correspond to some multi-particle state in the bulk. Okay, so the spectrum of vector models is very simple at the single trace level, and that's why they can be dual to pure, simple higher spin gauge theories of Vasiliev type. Okay. If we add a matrix type free theory, then we would still have some conserved currents schematically of this form. This is familiar in gauge theories, even in n equal 4 superior mills. They are the so-called twist 2 operators. They are conserved currents, and they will be dual to some massless gauge fields. But the spectrum of single trace operators in these matrix type theories is more complicated because there are also many more operators which are not conserved currents, okay, string any matrices, the number of matrices that you want, take a single trace, that's still a single trace operator. It should be dual to some single particle state, but it's not a conserved current. It's a massive state. Massive field in the bulk. So the dual to matrix type theories in the weak coupling limit should include both higher spin gauge fields and a very large tower of massive fields, while vector models don't have this feature. The spectrum is very simple. Okay. The other comment I wanted to make is about the restriction to singlet sector, which I sort of was doing by hand. I was declaring that I was only looking at operators which are UN or ON invariant. You can say that you do this by hand, but a fruitful, interesting way to think about this is that you should regard these UN or ON symmetries as gauged, and then it's natural to just look at gauge invariant operators and define these free theories as the free limit of a gauge theory, free limit of a ON or UN gauge theory. In 3 dimensions, we can do this naturally by coupling these vector models to Chern-Simons gauge fields. So we can take this model, just the Chern-Simons section. Let me write it down in the case of fermions. Okay, so you can start with this more general theory in which you include a gauge field, say a UN Chern-Simons gauge field, and then it's a gauge theory. You're supposed to only look at gauge invariant operators, and then you can define that theory to be the limit of this theory, where you send the 't Hooft coupling, which for Chern-Simons theory is n over k. This plays the role of a coupling constant, is like 1 over g squared. So that theory is the limit as lambda going to 0 of this theory. Okay, so that's one way to define what is the singlet sector of that theory. You start with, you gauge the ON or UN symmetry, and then you consider the free gauge theory limit. But this then naturally suggests that it may be interesting to study this theory more generally at finite lambda. Okay, so that's something that I'm not sure I'm going to talk about in detail. I don't know if I will have time. So you would expect that once you include this coupling and you keep lambda to be finite, you would expect that the higher spin symmetry is badly broken. But in fact, this does not happen. It can be shown in this vector type theories, where Chern-Simons is coupled to a vector model. It can be shown that even at finite lambda, the higher spin operators are in the large n limit are still approximately conserved. I'm not sure if you can all read this, but the structure here is similar to what I was discussing yesterday for the critical scalar. So what happens in these vector models is that the non-conservation equation for the current is always such that here you have a double trace operator on the right-hand side, and then this non-conservation is suppressed in the large n limit, and it implies that the dimension of these currents is still s plus 1 plus 1 over n, not the same f. So strictly in the large n limit, these are still conserved currents. So that led to the proposal that these models at finite lambda and large n are still dual to higher spin theories, so the higher spin fields are still massless at the classical level, still dual to higher spin theories. It's neither type A or type B, obviously, but it turns out that there are appropriate Vasiliev theories which fit the features of these theories. In particular, they break parity. So in 3-dimension, Chern-Simons term breaks parity. So we need some kind of parity breaking higher spin theory in AdS4. And there is such a theory. It's neither type A or type B. It's a theory which depends on some extra parameters which could map to this lambda. Okay, so so this point of view of thinking a little more carefully how to impose the singlet sector constraints led to some generalization of these conjectures, where we relate vector models coupled to Chern-Simons to some more general Vasiliev theories which break parity in AdS4. Okay. Any questions? Yeah.
So if I take a scalar and a fermion and add a Euclid, write down
Yes, then in that you will have fermionic operators in that theory. And yes, they at least in the free limit, you will have some higher spin theory which has both bosonic and fermionic higher spin currents. There are such theories, yes. Yes. Basically, for any free theory you can think of, there should be a higher spin theory. It may not be known at a nonlinear level, but you can identify the spectrum for sure. Yes?
About the free back type theory, you need to put about to build some high dimensional, high spin theory compatible on some internal manifold.
Sorry, I'm not sure I caught the question.
About the back type theory,
Matrix type, yes.
it is reasonable to build some high dimensional, high spin theory compatible on some internal manifold.
Um, well, so if you have, for example, n equal 4 super YAMLs, then we know it should be dual to type 2b string theory on AdS 5 cross S5. You can do a reduction on the S5. The statement is that that theory should be dual to some, in the weak coupling limit, should be dual to some higher spin theory in AdS 5, which has higher spin fields and a lot of extra operators. Some of them will come from the Kaluza-Klein reduction on the 5 sphere. Okay, so if there are no other questions, move on. And now we'll leave the CFT for a while and discuss something about higher spin gauge fields. Trying to hopefully move towards introducing Vasiliev equations. Okay. So let's start by reviewing something basic, which is equation for free higher spin fields. And let me start first in flat space. So the familiar examples are, of course, spin 1, which is the Maxwell theory, in which we have the familiar gauge symmetry and equation of motion, which are just this, or in terms of A, okay, so this is the equation, the free equation for a massless spin 1 field, or spin 2, we can think of linearized gravity. So, so we linearize the Einstein equation. By setting the metric to be, so I'm doing here first flat space. Okay, so then the linearized equation for the graviton which if you never derived, I suggest you do as an exercise. So if you linearize the Einstein equations around flat space, you get this wave equation for the for the fluctuation of the metric, which has the familiar gauge symmetry with a spin 1 gauge parameter. Okay, so how to generalize this to arbitrary spin? Writing down some gauge invariant equations for free higher spin fields. That was done by Fransdal. Okay, so Fransdal. 1978. So to write down gauge invariant equations of motion and Lagrangian for higher spin fields, Fransdal, well, I'm not going to derive this. He derived this starting from the massless, taking the massless limit of massive higher spin particles. I'm just going to give you the result. So these higher spin fields are described, and I will focus on the totally symmetric case. Described by fields which are totally symmetric with S indices, and they are double traceless. So double traceless means that if you take the trace twice, you get 0. This constraint is empty in the case of spin 1, spin 2, and spin 3, but it becomes non-trivial in the case of spin 4 and higher. So you have this constraint on the Fransdal fields, and the gauge invariance by generalizing what you know for spin 1 and spin 2, it's not surprising. Guess the following gauge invariance. Okay, with a spin S minus 1 parameter, and then the gauge invariant equation of motion found by Fransdal take the following form. So we define this tensor G, which is a generalization of the linearized Einstein tensor. Box minus S. So I'm just going to write down this in completeness, even though it may be a little painful, but just at least for free fields you should see what the wave equation look like for higher spin fields. Okay, so that's the equation that Fransdal found, and you should try to take the gauge variation of this equation of motion using that gauge transformation to show that the gauge variation of this is S minus 1, S minus 2 divided by 2, and here there are, okay, the details do not matter too much, except that here you get the trace of the gauge parameter. So in order for this to be gauge invariant, you have to restrict the gauge parameter to be traceless. Okay, so the generalization of the spin 0, spin 1 and spin 2 gauge symmetry involves a spin S minus 1 gauge parameter, which is supposed to be traceless for gauge invariance to work. Okay, and these equations can be derived from a Lagrangian. that was indeed, I think, one of the main points of Fransdal paper is that you can have some Lagrangian equation of motion for these massless fields. And the Lagrangian has the following form: O action Okay, so that's the Fransdal action, and again, similarly to here, you can verify that it's gauge invariant, and the gauge invariance requires both tracelessness of epsilon and double tracelessness of phi. So that's where the double tracelessness constraint also come from. It's for gauge invariance of this action. Okay, so that's the fully off-shell gauge invariant equation. Then we can fix a gauge and describe a simpler, as usual, a simpler wave equation for gauge fixed dynamics. And we can gauge fix, so gauge fixed on shell equation, we can gauge fix phi to be transverse and traceless. Then the equation of motion simplify to a usual wave equation which is, well, it may be called a Pauli-Fierz equation. Pauli and Fierz wrote something like this equation for massive spin 2. It is like a massless Pauli-Fierz equation. It describes a gauge-fixed version of Fransdal equation. If you study propagating degrees of freedom, you see that these equations describe consistently propagation of two helicities in 4 dimensions, plus minus s helicities. So these are consistent equations which describe propagations of massless higher spin fields of any spin in flat space. Okay. Now the question, so this is flat space, what happens if we want to put this, actually this is just ordinary derivative here. What happens if we want to put this on a curved background? So how do we generalize it? Your question? No. Okay, so what you would do to covariantize, of course, following the usual rules, you should replace derivatives by covariant derivatives. Okay, schematically. But if you do that, you'll soon discover that these equations are not gauge invariant anymore. There is no way to make them gauge invariant for an arbitrary metric. If you do this covariantization in the action and study the gauge variation, then you find that the gauge variation involves the Riemann tensor contracted in some way with phi and the gauge parameter. Okay, I'm in schematic here. The point is that the gauge variation involves the Riemann tensor. And for general, completely arbitrary metric, there is no way to compensate that. Okay, so it's not possible to make these higher spin equations consistent in an arbitrary background, except for spin 1 and spin 2, of course. And that is expected because if we were able to do that, it would mean that we could write down consistent interactions of higher spins with gravitons. But in flat space, there's supposed to be no non-trivial S matrix for higher spin particles interacting with gravity. So this is physically is related to that. Here technically you see that these equations cannot be made gauge invariant. Okay, so the only way out is when this Riemann tensor is very simple, like a maximally symmetric space. Then this Riemann tensor is a product of two metrics. And then this variation just gives some mass-like terms in the Lagrangian, which you can cure by adding some extra quadratic term in the higher spin gauge fields. So I think this cannot be seen very well. So only possibility is a maximally symmetric space. So of course flat or de Sitter or anti-de Sitter. Okay. Then the action can be made gauge invariant provided you slightly correct this tensor that I defined there. So let's say it will be the covariantization plus a correcting term which is quadratic. Okay, let me omit the detail here. So it's a correcting term which is linear in G, and it will give an extra mass term in the Lagrange. Okay, the physical important point is that you can make this higher spin massless particle propagate consistently only in flat space or anti-de Sitter space or de Sitter space. In general space, you don't have gauge invariance, and then you cannot decouple them physical polarizations of these particles. So it will describe an inconsistent theory. Any question? Okay. Okay, so let me not write down the full correction here, but let me just write down the gauge fixed equations in AdS. Yes?
What's around the corner? We can't actually see what's
Oh,
we can't actually see the end of that equation.
you cannot see here. Yeah, so it's just a linear term in phi with some coefficient which depends on the spin and the dimension. So you correct this G that I wrote. First you covariantize the derivatives, and then you just add the correcting terms, which is linear in phi. Okay, all right. When you write down the gauge fixed equations in AdS, they look like this. In AdS d+1, this is the full Franzdal of shell equation I won't really need, but this may come back later. So once you gauge fix it, the equation looks like this. Okay, so this mass-like term which appears here arise from this correcting term that you have to put. But it's not really a mass. It just comes from the coupling to curvature. I'm setting the curvature radius to 1 here. So it's not a mass. It's just the precise value that it's required for gauge invariance in AdS or in DS. Okay, so here I'm already specializing to AdS. If it's DS, it will be opposite sign. Okay. And this D that I wrote here is D+1. Okay. Okay, so these are the on-shell equation, gauge fixed equation describing massless higher spins in AdS D+1. You can study, for example, take a Poincaré metric of AdS and study how the solutions to these equations behave when you approach the boundary. So what you find, so take in the Poincaré metric, then phi, just being schematic here, for small z behaves like the delta minus s, some alpha, which only depends on x. And this delta, so by solving these equations, you find an some quadratic equation for delta, which generalizes the one for scalars that I wrote in the other lecture, and looks like this. Where k is this. Okay. And then you find that the solutions are indeed corresponds to delta equal s plus d minus 2, which is the dimension of a conserved current in the boundary theory. And there is another solution, which is 2 minus s. Okay. So for spin 0, for example, these are the two solutions which for in d equal 3 would be delta equal 1 and delta equal 2. For spin 1, these are the two possible boundary conditions for the spin 1 field. For higher spin fields, we usually don't impose these boundary conditions, but you actually can also do that. You will describe some induced conformal higher spin theory at the boundary, but I'm not going to discuss that because I don't have time. Okay, so for the usual versions of the duality, we will choose this boundary condition for the higher spin fields, which corresponds to having these conserved currents in the CFT. Okay. All right. Any questions so far? Okay. You can get it. Okay, so this Fronsdal formulation of higher spin fields is called sometimes metric-like formulation of higher spin because it's a natural generalization of this equation for the fluctuation of the metric. Now, it's a nice formalism to write down free propagation of higher spin fields, but it turns out to be quite hard to write down interactions in this metric-like framework. So cubic couplings were written down in this metric-like formalism in AdS, but not a fully nonlinear theory. So what Vasiliev realized is that it's more convenient to adopt a generalization of the so-called frame-like formalism, which is instead of metric, we use Wildbein and spin connection in gravity, and use the language of differential forms. And if you do that, at the free level, you recover something equivalent to Fronsdal, but it's then easier to write down nonlinear equations. So I'll try to discuss that now. So frame-like formalism. Okay, so recall that in gravity, we can write down gravity instead of in terms of metric, in terms of Wildbein and the spin connection, where the mu's are so-called curved indices, and A and B are the flat indices, the frame indices, and we have a local Lorentz invariance, and this omega is the gauge field for that. And then it's natural to combine this Wildbein and spin connection into a single one form, which I'll denote as W. So this W here, N, A, B are the generators of the local Lorentz rotations, and PA are the generators of the translations. Okay, so the algebra, so if we are working with negative cosmological constant, the algebra satisfied by this PA and MAB is the AdS algebra. In D equal 3 would be SO3, 2. So M are just the usual rotations. P transforms, or M rotates P. Okay, so this will be the same in zero cosmological constant. The one which is different is the commutator of the translations. So this is the AdS scale, which usually I set to 1, but I'm putting here for clarity. Okay, so this is the SO3, 2 algebra. In the flat space case, we could do the same construction, then PA and MAB will generate the Poincaré algebra. This will be 0. And in the de Sitter case, you just have an opposite sign here. Okay, so we can combine E and omega into a single SO3, 2 gauge field if we are discussing gravity with negative cosmological constant. And we can, as we do usually in Yang-Mills theories, we can compute the curvature of this gauge field. And this, which is a simple exercise that I leave to you, using that algebra and computing this curvature, you get a term proportional to the P generators, which is nothing but the torsion. And you get another term which is some kind of generalized Riemann tensor. This is just the usual Riemann curvature 2 form. And then you have this extra cosmological term, which comes from this commutator. So if this was 0, this wouldn't be there. Okay, so this is the curvature of this field. And then you recognize that a maximally symmetric background in this formalism is just a zero curvature background. Okay, so the zero curvature condition gives AdS solution. Or de Sitter if you're doing the other sign of the cosmological constant. So this is just a torsion constraint which allows you to solve omega in terms of E, and this is just the condition that the Riemann tensor is related to the metric, essentially. Okay. Okay. So this, indeed, we'll see later. It's precisely the way in which the AdS solution, AdS background, will arise from the Vasiliev equations. So that's something to keep in mind. So now, Vasiliev idea is to try to generalize this construction to all spins by including all spins at once into some gauge field W, like this. So make some bigger algebra in which we don't have just P and M. We have an infinite dimensional algebra with all the higher spin fields. And the most convenient way to introduce Vassiliev formalism in 4 dimensions is to use two-component spinors notation, which I'll just briefly review, but I assume most of you know about. So before we go on, just a quick reminder on two-component spinors notation in 4 dimensions. So this is just a statement that using Pauli matrices we can convert a vector index into a bispinor index. So for example, XA we can convert to X alpha alpha dot by using the Pauli matrices, where sigma A is 1 and sigma vector are just the usual Pauli matrices. So this is just, I hope, a familiar thing that you can do in 4 dimensions. It's basically a form of the isomorphism SO4 equal SU2 cross SU2. So you can split one vector index into the product of 1/2 0 and 0 1/2 representations of SU2 cross SU2. So if we use these notations, okay, the Wildbein, which I was writing as EA, will be E alpha alpha dot, and antisymmetric tensor omega AB will split into omega alpha beta and omega bar alpha dot beta dot, where this is totally symmetric. Okay, you can count that the number of components that you have here, which is 6, is the same as the sum of this plus this, which is 3 plus 3. Okay, and so on. You can convert all representations in the vector notations to some spinorial language. Okay, so this turns out to be a convenient thing to do, to write down the equations. So next, where did I go? Okay. Next, we introduce some auxiliary twistor variables. And it will be clear in a second why we are introducing this. So introduce a pair of twistor variables which transform in the spinor spin 1/2 representations, but they are commuting. And on these spinors, we introduce some star product. Star product.
Should we think of these variables as being tangent to space-time or something like that? Will you suggest how this number?
You should think of this as exactly as, well, products of this will be related to those generators. So they are like more like fibers for the space-time. So the reason why I'm introducing this is just a convenient way to realize that algebra and then to extend it to higher spins. So introduce this. By definition, introduce this star product, and the same for BART. Now in the literature here you'll find different conventions for this, but for the purpose of these lectures, factors of I are not so important, but maybe a more common convention will have an I here. Okay. Okay, so more generally, this is just like if we have a star product between two functions, I'm afraid this cannot be read easily. Okay, by this CC I just mean the same term for the barred variables. So you have this Moyal-like star product. It can also be represented in integral form, which is a representation which is often useful for calculations. Okay, so this is a formal. I'm assuming that there is a choice of contour here so that this integral converge in particular. So this is defined so that this is true. Okay, contours and normalizations are chosen so that this is true. And this UV just means U alpha V alpha, where the spinor index are higher than lowered with the epsilon symbol. So this is similar to what similar to the formalism that Nima was describing yesterday in his lecture. Okay, so now it's easy to see that if you consider bilinears of these y's and y bars, and we call p alpha alpha dot, y alpha, y bar alpha dot, up to normalizations. So if we look at bilinears of these twistor variables and we consider their commutators under star product, we see that this star product is defined precisely in such a way that we reproduce the SO3,2 algebra in these two component spinor notations. So for example, M alpha beta, M gamma delta star commutator. So this just means this M star this minus the other way around. So it's a commutator with the star product. If you do that star product, you see that, so you can use the star product to contract two of the y's, and then here you'll get an epsilon times an m plus minus the other terms. Okay, so this is the two component spinor form of this here. And if you do the other commutators, you reproduce all the rest. For example, P alpha alpha dot, P gamma gamma dot, star commutator. So in this case, well, I should perhaps say there that, so I wrote y star y and y bar star y bar. Y star y bar is just the ordinary product. You can see that from the general definition that I wrote there. So the star product of y and y bar is trivial. So here we get the star commutator. We get epsilon alpha beta m bar alpha dot beta dot plus the other term. Okay. So far these twistors, I just introduced them as a way to realize this SO3,2 algebra using star commutators.
Are there relations between representation Y and representation
Of P and Q?
P and N?
Well, I mean, P is a vector, right? So it's a product of the alpha and alpha dot representation. I can't see. I mean, I don't know if I got the question right.
Well, the sort of context of the thought
Yeah.
of my question was,
Uh-huh.
so if you have y, then you can construct p and m. But
Yes.
so for example, suppose you have any representation of p and m, can you reconstruct that from y or vice versa?
I mean, I'm just realizing the algebra. So this is a representation of P, is a particular representation of P. Okay.
I can think of why alpha is the oscillator relation phase. Oh, switch on to two.
Sorry?
I can think of why oscillator relation is low switch on two.
As what?
Oscillator relation.
Oscillator.
I think that
Yes. Yes.
Might a partial answer to Hiroki's question be that if you take that fixed quadratic expression, those fixed quadratic expressions for P and M, that if you then act upon polynomials in Y, say symmetric polynomials with
Right.
indices, that gives you at least a large class of representations of the Lorentz algebra, unitary ones.
Yes, so this in particular, this M will act as a rotation on those indices. If you take the commutator of M with an object with more Y's, it will act as a rotation generator. Yes. It just follows from this definition of star product.
These won't be unitary representations, though, since they're finite dimensional. You're representing the non-compact group SO3 too.
Yeah.
So it's unitary representations with the infinite dimensional. So it's true that degree k polynomials in Y give representation for every n.
Yes.
More exactly, degree k polynomials in Y and Y bar together.
Yeah. Well. Okay. Let's see how to extend this to higher spins. So, okay. So in this language so far, this just means that we can, instead of writing abstractly W in that form, we can think of W, for the spin 2 part, we can think of W as a one form which depends on space-time and extra auxiliary coordinates such that it's quadratic in Y and Y bar. So this will be spin 2, gravity and Wilbanian spin connection. But then it's natural to generalize this to higher spin by simply saying that we consider an arbitrary function of Y and Y bar, including all possible powers. And the expansion of this function in all possible powers will, the coefficient of that expansion will be fields of higher spin. So if we have bilinear, we just have fields corresponding to spin 2. If you allow all possible powers of Y and Y bar, we encode higher spin objects inside W. Okay, so as I can. Okay, so for higher spin now, So allow this to be a general function of y and y bar. Denote as an n comma m, where n denotes how many y's are there, and m how many y bars are there. Okay, so we have this expansion, and these coefficients are fields, function of x. So the bilinear part should just be gravity, and in general, the term here, which has n minus n plus m equal to 2s minus 1, corresponds to a spin s field. Okay, this y is carry spin 1/2. This, you should remember that is one form, so there is an extra index hidden here, a mu, dx mu. And then this, packaging this w in this way gives a generalization of the Wilbine spin connection formalism to all spins. So in particular, so just to clarify this, I think I write down So first, trivially, we can also include s equal 1 here. It will be the term which is independent of y and y bar. It's just the one form. So that's w0, 0. S equal 2 is the one we already described. It will have 1, 1, 2, 0, and 0, 2. This is the Wilbine, and these are the spin connections. Okay, now for a higher spin, for example, spin 3, you'll have 2, 2, 3, 1, 4, 0, 1, 3, 0, 4. Okay. This object here, which is an object which looks like E mu alpha 1, alpha 2, comma, alpha 1 dot, alpha 2 dot. This is the, yes? Did I?
Spin 3 rather than spin 4? I haven't learned how to track these.
Yeah, okay. So n plus m is 2s minus 1. Okay, so you can think of making this, roughly speaking, you can think of making any pair of alpha alpha dot as a vector index. So here you have, sorry, this is an m. And then you have an extra mu there. So, because this is a one form, right? So that's where the minus 1 come from, and the 2 is because each of these carries spin 1/2. Okay. So you see, for example, gravity, it's not 2 but 1, 1, right? That's the Wilbine, E alpha alpha dot. And this is the spin 3 Wilbine. It has one vector index and alpha 1, alpha 2, alpha 1 dot, alpha 2 dot. And all these guys are generalization of spin connection. I don't want to go into too many technical details. It's just supposed to give an idea of why this is a natural way to generalize the Wilbine and spin connection formalism to all spins. Okay. Yes, at this level it can. So if we're describing a bosonic theory, there will be a constraint that this W is an even function of y and y bar. But you can encode half integer spins. In fact, this spinor formulation makes that very easy because you just have odd functions of y's, those will be half integer spins. Okay. So in general, the component which has s minus 1 alphas and s minus 1 alpha dots it's like the Wilbein. And after fixing the local Lorentz rotations, you can relate this to the Fronsdal field. In the same way as you can go from the Wilbein to the metric, you can go from this Wilbein-like formulation to the Fronsdal field at the end of the day. Okay? How much more time? 10 minutes? Okay. So as SO3,2 is the algebra of bilinears of these y's and y bars, the higher spin algebra can be defined as the algebra of polynomials, of all polynomials of y and y bars. It can be generated by all the monomials. And W is a gauge field for that algebra. Its gauge transformation, it's the usual one. You'd have a gauge parameter which itself is some gauge parameter which depends on x and these extra variables which play the role of the gauge group generators, right? Plus commutator. So this will be the gauge transformation associated with this W. And if you consider linearized gauge symmetry around AdS, which I haven't shown yet it's a solution of, I even wrote down Vasiliev equations, but just to anticipate. If you look at this gauge transformation, and here you put the AdS vacuum, and then this gauge transformation, you can show that it matches upon the Fronsdal gauge transformation. Okay? It's just basically will be the covariant derivative on a spin s minus 1 gauge parameter, if this is a spin s part. Okay? All right. So one important thing about this extension is the fact that we have to include all higher spin fields at once. So that is something that I already said last time. So it's an important feature. And it's related to the fact that once we introduce generators of spin greater than 2, so once we allow something which is more than bilinear, then this algebra doesn't close unless we include all spins. So this can be seen in the following way. So this higher spin algebra is the star algebra of these general functions of y and y bars. It can be generated by monomials. So for example, this term of spin S1 would be terms of this type where n m with n plus m equal to, sorry, this you can see, n plus m equal to s minus 1. So take these generators and try to look at their commutators. Say you take the star commutator of this with some S1 and S2. Then if you use the rule for the star contractions, you find that this is a sum of generators so now you see that if S1 and S2 are 2, which means you're just considering commutators of bilinears, you just get bilinears on this side. So that's the SO3,2 closed subalgebra of this big algebra. But as long as you add something which is greater than 2, you generate some other monomials. For example, if you take a commutator of a 2 spin 3 object, star commutator, here you will get P4 plus P2. So you generate a spin 4. So if you have spin 3, you have to have spin 4. And you can go on. If you have spin 4, you have to have spin 6. And the algebra does not close unless you include all of them. Okay? So one can also see that there is another closed subalgebra, but it's still infinite dimensional. It's a subalgebra of even spins. So that corresponds to the fact that we can truncate this algebra to even spins only, which corresponds to ON models at the boundary. So there is a subalgebra with even spins only. For instance, if you look at the commutator of P4 with P4, you get P6, P4, and P2. Okay. Here, so this is for any of those terms schematically. It's not an exact, so you can take any of these terms such that n plus m is 2s minus 1. You'll generate these spins. So this just counts the spin. Yeah, I'm not some. Yeah. Sorry? Yes, there's all the generators which are associated with spin s are those such that n plus m is 2s minus 1. So for example, for spin 2, there will be p and m. I will call them spin 2 generators. Any other question? Well, I didn't really yeah. If the cosmological constant is 0, there is no way to make this. I mean, the limit is singular if you send r to 0. Here I'm setting r equal 1, but the interactions will be singular. They will involve inverse powers of radius. Okay, I don't think I can introduce Vasiliev equations in the next 4 minutes. So maybe I'll stop for more questions.